Hi everyone, so let us look at a manometer. So for a manometer, we have three things to pay attention to. So this is an example of a manometer, and this is an example of a manometer. So this is a manometer. This is a manometer. This is a manometer. In fact, I showed you all a manometer in class. So let's see what is going to happen here. For manometer, we have three things to pay attention to. The pressure change for a manometer is calculated using this formula. So the change in pressure for a manometer is calculated as what? Density of fluid, acceleration due to gravity, and the height of fluid. So that is the formula for pressure difference, or you may call it pressure variation, or you may call it change in pressure. For a manometer, the pressure at the bottom in the manometer is bigger than the pressure at the top of the manometer. And lastly, you must know that 2 points at the same elevation for fluid which is at rest are having the same pressure. And then, those are the three things you must know for a manometer. And for a manometer, we have to use 2 points and determine the pressure between 2 points. It's some kind of similar to what we did in Pascal law, but the difference is that for Pascal law, the fluid was actually at rest, but here it is not almost the same case, in the sense that one of the sections in the manometer can be open, but for a Pascal law, both sections were closed. You know, we have a piston, and the piston was in a cylinder whereby there was a load, masses at both ends of the cylinder. So basically, a Pascal law is just something like this. You have a piston, which then a force can be applied, and you have a piston that is carrying a weight, a mass, and we have F2, A2, point 1, F1, A1. So F2, A2. So that is some kind of a Pascal law. You could see that the fluid is not open. But in this case, we can have a fluid that is open, we can have a fluid that is closed, and the fluid is not at rest in most cases. So, but let us look at this context. So the technique to solve problem here is very, very clear. For manometer, when the fluid is in the manometer, we have to pay attention to the direction in which the fluid is moving. If the fluid is moving downward, the pressure difference is positive. So this change of pressure for fluid that is moving downward is positive. That is for downward direction. And for a fluid that are moving upward, the pressure difference is negative. So this is for upward direction. That is the main technique you need to use to establish your formula for a manometer. So let us look at the manometer. We have to consider 2 points. For Pascal law, we were using 2 points, and we use this formula F1, A1 equal to what? F2, A2. For a manometer, this formula cannot work. It cannot work. That's what I was trying to explain. For a manometer, we have to consider point 1 and point 2 as two separate points. We must say point 1 if we need to find the pressure for point 1. We have to be looking at the movement of the fluid. And if the fluid is coming downward, the pressure difference or pressure variation is added, is added. If the fluid is moving upward, the pressure difference is subtracted. That is just a technique. So see, in this case, we have fluid 1, we have fluid 2, we have fluid 3. But we know that they have the same gravitation and they have different height, H1, H2, H3. So for this manometer, we could see that it is open to atmosphere, so we have pressure atmospheric because it is open to atmosphere, so we have atmospheric pressure at the top. Plus what? Because the fluid is moving downward, we have positive pressure difference. Density of fluid 1, G and H1. Plus what? Density at fluid 2, G, H2. Plus density for fluid 3, G, H3. That is the pressure at point 1. You could see that it is just based on this technique which I said. Look at the pressure variation movement. Is it moving downward or upward? You could see that is the fluid movement. Remember, a fluid moves, and the sign of gravitation is the main quantity that changes the direction. Now, if a fluid is moving upward, we know that G is equal to what? Negative. There is negative gravitation for a fluid that is moving upward. For a fluid which is moving downward, we have positive G. And that is what speaks to this equation and this equation. Now, let us look at this manometer at figure 241. We have to consider 2.1 and point 2. So point 1, the pressure at point 1 is equal to what? Is equal to the pressure at point 2. It is point 2 and point 1 is not open to atmosphere because it is inside a tube. It is inside a tube. Inside a tube. It is inside a tube. Inside a tube. So P1 plus what? Because the fluid is coming downward, we have what? Density 1. We have G is coming downward into what? This plus this, A plus H. Now we are coming to fluid 2 is going upward. So we have what? We have negative. We have negative the density rho GH, because G is negative, is going upward. And what is the height? This is just the height for that fluid. So this red fluid has a height of what? H. Be careful. Why for this water it was this height plus this height. Why for the red fluid it is just this H. So that's what we have. Density for fluid 2 GH. And now we are moving now to what? Let me be careful not to get you confused. Density 2 G then H. At this we have the fluid is still water, so we have density 1. So we're gonna have, because it's going upward, we have what? Negative density 1 G, and it has this height. It has the height which you see here, which is A, equal to what? P2. So that's how we establish that formula. So, and it's quite an easy formula to write if you're able to remember what I explained here, because that is just because of the gravitation. Now, let us look at an example problem. We need to determine the air pressure in the tank. So effectively, we are going to calculate P1. We are going to calculate P1. Remember, this is open to atmospheric pressure. P2 is equal to atmospheric pressure. You must be able to see that because this tube is open to the atmosphere. So, but the first thing here, step 1, write the equation for pressure at P1 and P2, which is what? P atmosphere, because we must always write the pressure between 2 points, which I indicated. And in this case, we have to write the pressure between point 1 and point 2. So remember the concept we're using. Pressure at point 1 is equal to what? Is equal to density for water. It's coming downward, so we have positive G. G times H1 plus P1 plus P1 plus what? Now we have oil is coming downwards. Water is coming downward. Oil is coming downward. We have density for oil G H2. This is the height. Remember, this is the reference height we are using. H1, and this is for oil. That is the height for oil. Oil is H2. Now we have mercury. Mercury is going upward. Mercury is going upward. So we have negative G for mercury. So therefore we're gonna have what? We're gonna have negative pressure difference or negative pressure variation, which is density of mercury G H3 equal to what? P2. And that P2 is equal to what? P atmospheric pressure. That's what we have. And therefore, what are we solving for? We can solve for P1. So therefore, P1 is equal to what? It's equal to P atmospheric pressure minus density of water times G times H1 minus density for oil H times G times H2 plus density for mercury times G times H. So this becomes the formula for the pressure in the tank, which is P1. That becomes the formula for the pressure in the tank, which is P1. So therefore, we know that the unit is not of a bigger problem here. We know that P1 is equal to what? It's equal to atmospheric pressure, we have 85.6 kilopascal, if you look at the question, plus we have G is 9.81, so G is, so the density of fluid is, we have density of fluid, we are looking at water, is 9.81 meter per second square. And then what do we have? We have 13,600 kilogram per cubic meter times 0.35 meter minus 1,000 kilogram per cubic meter times 0.1 meter minus 850 kilogram per cubic meter times 0.2 meter, and we are going to multiply by 1 Newton over 1 kilogram meter per second square times 1 kilopascal over 1,000 Newton per meter square. Remember, 1 Newton is equal to what? 1 kilogram meter per second square, and 1 kilopascal is equal to what? 1,000 Newton per meter square, and we're going to have our answer. P1 is equal to what? 130 kilopascal. So this is the pressure, the atmospheric pressure. This is density of water, like you see in this problem here. We have atmospheric pressure, we have the density for water, we have density, so this is density for water, this is density for oil, and this is for density for mercury. So if you look at the formula carefully, then this is density for water, and therefore we have gravitational acceleration, which was this is actually G, which is acceleration due to gravity, and this is the density for water. No, this is density for mercury. This is density for mercury. That is density for mercury, and this is 1000. This is density for water, and this is density for oil. This is density for oil. So that's what it is. So see you on Monday, see you on Tuesday, and have a wonderful rest of your day. Thank you.